So, as you can tell, I graded the test. Oh, you know what? I didn't enter any of these grades into a database. So, you know what? If you could just email me your grade, I would appreciate it. I know what the grades are. I just need to put a grade with a name. So, this was the breakdown of the test. I think these people, go from master of the material to probably understand, but maybe just made some goofy mistakes. These people are kind of on the fringe of understanding, or maybe just ran out of time, or these people, I would call this like the B group of test grades. This would maybe be the A group and the B plus group. This group I think probably needs to review a little bit more, but I think just review more and more practice. Maybe more sleep. And this group is the only group that I'm really concerned about. And this group, this score was doubled, so I would have a hard time giving that one an A and this one a B. So for people in this group, I think what we've done so far is we've laid the foundation. Okay, we're going to be laying a little bit more foundation, like backstepping is another foundational tool. But we're going to be getting into a phase where we're doing just design. And it's going to be examples of one of. There aren't like 10 homework problems that I can assign that go over how to design a high gain observer. There's maybe 5 results in literature that go over the technique that I'm going to be presenting. So these are pretty advanced concepts. So I think for people in this group, the best thing to do, I definitely want this group to move up into here. And we've got plenty of semester for that to happen. So there's no reason to get discouraged or depressed about anything at this point. But just let it be kind of a warning that, you need to practice more. Maybe you need to have a study group. Maybe you need to come talk to me more in my office. Maybe you were sick. Maybe you were trying to get a paper published and you didn't sleep for 2 days before. Those things are immediately taken care of. But if it's something more fundamental, then we're going to be relying on this, we're just going to be building on this foundation. So make sure that you understand where your errors were and that you examine what was the problem and try and fix it. Because I really, really want this group of people to move this way. Okay? So overall, I was really happy that we had so many students, because I thought the test was actually fairly challenging. This is probably the hardest test I've given the whole time I've been at the University of Florida. So all the other tests I've given since I've been here have been kind of softballs. They're just lobbing it up there for people to hit out of the park, and been sadly disappointed when people whiff. But this one was actually, had some challenging parts to it. And so I expected more of the grades to be in this ballpark, which the bulk of the class was. But clearly there's a group that is really, really catching on well. So I was happy with that. This was a little concerning, but not too bad. It was the first test. We got plenty of semester to go. There's plenty of room to change all that. So I'm not overly concerned about that either. Okay, so I think it's probably more instructional at this point to go through the test in detail rather than go back to the last lecture and continue with our backstepping example and then do the test. So even though we're almost done with the backstepping example, that one anyway, but I think it's better for me to spend a day going over the test And then the next class, we'll kind of backtrack a little bit and maybe start that last backstepping example over again and just really make sure that everyone is on the same page with backstepping. All right, so go through the test. So I guess one final comment is, this is a graduate level class, so, I don't really believe in knocking people over the head with a ton of homework, and I believe the students should be mature enough, and, especially if you're doing a PhD in control, you should just want to do this stuff. This stuff should set you on fire, make you excited about doing it. So I don't have to make you do homework. You can search things out on your own. And likewise, I'm not trying to punish you on the grading or punish you with a grade, because I know some of you aren't doing nonlinear control research for your PhD. Some of you are taking this class just to kind of complement your skill sets. And, I don't want to punish your grade point average, but I do want you to, make sure you're kind of keeping up with the bulk of the rest of the class. Like I said, for a grade that's doubled, it's hard to justify that. But, I think there's plenty of class left to make up a lot of grades. So the first part was find the equilibrium point. And I was happy that every single person in the class said find the equilibrium point means set the x dot's equal to 0 and solve for it. So from this equation, you immediately get that x2 has to equal x1. And from this equation, you get 0 equals, you can bring over the x1, so I'll do that. You get x1 equals, now x2 equals x1, so I'm going to write minus x1 on the 1 plus 2 cosine squared x1. And with a little bit of math, you can solve this problem and find out that the only way this is possible is if x1 is 0. So x1 must be equal to 0. And if x1 is 0, then this means that x2 is 0. And so it appears that this is the global equilibrium point. Okay, now I restricted the domain on the test, and if you have to work in a restricted domain, then you can't claim that you get a global stability result. However, since this is the global equilibrium point, I didn't think it was right to take off from your test if you said global asymptotically stable. So I let it slide if you wrote global or local, but in the strictest sense, given a restricted domain, so just so you know, if you're given a restricted domain, it cannot be a global result. But since this was global, I just didn't feel right taking off for it. All right, so then we had to find the stability of this. So I gave you the Lyapunov function was 1/2 x1 squared plus 1/2 x2 squared. So v dot was equal to minus x1 squared minus x2 squared on a 1 plus 2 cosine squared x1. Okay, so, well, first of all, this is a positive definite, radially unbounded function. It's autonomous, so we don't talk about decrescent because it's obviously decrescent. So we just have to check if v dot is negative definite or negative semi-definite. So we got negative, so this piece here is always positive or 0. So we can just get rid of that piece and drop it out altogether and write that v dot is less than or equal to minus x1 squared minus x2 squared. Okay, so at this point, I would say 90% of the class said that this is negative definite and they said gas. This is a true statement, but it's not the complete picture. Okay? So for people who did this, I took off 3 points because the more correct answer is GES, right? Because you've got x1 squared, x2 squared here. So x1 squared plus x2 squared is equal to 2v. So this is less than or equal to negative 2v. Okay? So you can get global exponential stability. Okay? So on the B part, I took off I took off this minus x1. So this minus x1 was really sweet to put in there, right? Because it gave us our negative x1 squared, and it gave us our negative definite result. So we were feeling pretty happy when we see that. But then in the second problem, I changed it to x1 dot equals x2, x2 dot equals minus x1 minus x2, 1 plus 2 cosine squared x1. And v equals same thing. V dot is the same thing, except for now, we don't have our happy negative x1 squared there. And so some people got confused about this, but again, this is always a positive term multiplied by always a negative term, so we can just get rid of it. So we can say v dot is less than or equal to negative x2 squared. And this is a negative semi-definite result. And so some people, just a few people, stopped here and said, okay, it's stable. It's globally stable. But what you should have done is you should have saw this and said, wait a minute, it's negative semi-definite. However, I have a tool because this is an autonomous system and I can use LaSalle's invariant set theorem. So let me examine this further. And if you examine it further, v dot can equal 0 only if x2 equals 0, which means x2 dot will equal 0. So I go up here, and if x2 dot is 0 and x2 is 0, then that means that x1 has to equal 0. Okay? So this means that x1 has to equal 0. So the only way that v dot can equal to 0 is if x2 and x1 are equal to 0. So this is LaSalle's invariant set theorem. And then from this, you can get gas. Okay? Any questions about the first problem?
That's not the corollary, that's the actual LaSalle's.
Well, that's the corollary, yeah. Which is the useful. Okay? So the second one really, I didn't make out the solution when I was designing the problem. I just threw a bunch of functions up there, and it turned out to be probably more challenging than I expected. And a lot of I was happy because it exposed a lot of confusion on people that we need to flush out right now. Okay, so this was the first function. And so the first thing you had to ask yourself is this radially unbounded? So it can't be radially unbounded. It's radially unbounded with x1, but it can't be radially unbounded because x2 is saturated here. You know, we did an example in class where you had this as saturated because if x2 goes to infinity, you get infinity over 1 plus infinity. So this is always less than 1. So it can't be radially unbounded. So is it positive definite? So for it to be positive definite, this is a non-autonomous function. So for it to be positive definite, it has to be lower bounded by a positive definite function. Okay. So in order to lower bound this, we know that we can lower bound cosine squared by 0. So w is less than or equal to x1 squared plus x2 squared over 1 plus x2 squared. So this is a positive definite function. A positive definite autonomous function. So because this is true, it is positive definite. And since it's positive definite, then it can't be positive. Well, like I said, by definition, it's positive semi-definite, but you would never say that. You would say the stronger case that it's positive definite. All right, so then the other question was, is it decrescent? So in order to test if it's decrescent, for a non-autonomous function, you had to look and say, is it upper bounded by a positive definite function? And for sure it's upper bounded by a positive definite function, because as the biggest cosine squared can get is 1. So this is upper bounded by 2 x1 squared plus x2 squared over 1 plus x2 squared. Okay, so because you can develop these two inequalities, then W is positive definite and decrescent. And that was it for that one. So the second example was x1 squared plus cosine t x2 squared. So the first question is this radially unbounded? Well, the first question is this an autonomous function or a non-autonomous function? And the answer to that is it's a non-autonomous function because it has an explicit dependence on time there. And for it to be radially unbounded, then W has to be lower bounded by a W1, a positive definite autonomous function, and W1 has to be radially unbounded. So we can't, because cosine t can be 0. And so so first of all, we can't lower bound it by a positive definite autonomous function. So in the beginning, we know that it's not positive definite because we can't lower bound it by a positive definite autonomous function. And because we can't lower bound it by a positive definite autonomous function, then we can't say it's readily unbounded either. And you can just look at this and tell it's not readily unbounded because cosine t can be 0 or negative, and irregardless of what x2 is doing. So it's not positive definite. In fact, you could look at this and say, well, since cosine t can be negative, W is isn't even guaranteed to be a positive thing. So much less positive definite. So it's not positive definite, and you can't even say it's positive semi-definite because it may be negative because the cosine t term's sitting there. Okay, so it's not even positive semi-definite, and it's not radially unbounded. Now, is it decrescent? So for it to be decrescent, we would have to upper bound W by W2, some positive definite autonomous function. So can I upper bound this by a positive definite autonomous function? I sure can. I can say W is equal to W2 is equal to x1 squared plus 2 x2 squared, for example. This surely upper bounds that, because cosine t, the biggest it can ever be is 1. Or I could pick lots of different things here for W2. So because I can develop this W2, it's decrescent. All right, so the third one is x1 squared onto 1 plus cosine squared t plus cosine x2 squared. Okay, so it's a non-autonomous function. So we have to start asking ourselves, can I develop a W1 and W2 that are functions of just x? So because I need this W1x, and I need W1x to be radially unbounded in order for this thing to be radially unbounded. So I look, nothing in here concerns me, because the cosine squared is always positive, it's lower bounded by 0, but I still have my x1 squared term there, so that's not a concern. But this is a big concern, right? Because again, I've just got a regular cosine element in here, and just like in the previous problem, this was cosine t, which could be negative. I don't know that this is positive or not. Cosine of some number could be negative. Yeah, maybe x2 squared is 3.14. And get negative 1 there. Maybe x1 is 0, and maybe x2 is the square root of 3.14. So then w is negative 1. So because w can be negative 1, then I can't say, so it's not positive definite. Since it's potentially a negative function, it's not even positive semi-definite. And because I can't develop this W1 term, it's not radially unbounded. And you could have looked at the cosine x2 squared term and seen that that wasn't going to be radially unbounded anyway, because there's no way x2 can go to infinity and w wouldn't go to infinity. So it was, you could have seen that from a couple of different angles. But is it decrescent? Is it decrescent? Surely it's decrescent, because I can pick w2 equals x1 squared plus x2 squared, and that's bigger than w, and it's a positive definite autonomous function. So because I can pick this, it's decrescent. Okay, so let's go through all 5, because maybe the explanation will answer any questions, and then I'll field any questions that you guys have. So the fourth one is x1 squared plus e to the negative t. Immediately we see that we don't have x2 in here. So we know that we can't lower bound it by w1. So we know it's not positive definite. However, e to the negative t will always be positive. So at least w is positive. So we can say that it's positive semi-definite. Yeah. And what about decrescent? Sure, I can pick w2 equal x1 squared plus x2 squared plus 4, if I want to put a plus 4 there. Because this e to the minus t, the biggest it can be is 1. So the biggest this thing can be is x1 squared plus 1. So I could put x1 squared plus 4, or I could put x1 squared plus 1. But then I could just add x2 squared in there. This is always positive, so this doesn't reduce it any. So so this is decrescent, because this is a positive definite autonomous function. Okay?
So, is W2 positive definite if it's not 0 at 0?
Surely yes, but I have to think about it. That's a good point. Let me think about that. That's a good point. I'll have to think about it.
Not that I want the results to change. I got this one right.
So then the fifth problem is x1 squared on the 1 plus e to the negative t plus tan inverse x2. So unfortunately, we've got this tan inverse thing sitting here, which, as I drew during the test, has a shape like that. And because it can be negative, then this term here, in fact, for pi over 2, it can be negative infinity. So I've got a giant negative term over here. So right off the bat, I know that it's not positive definite and it's not positive semi-definite. And then I have to ask myself, is it radially unbounded? Well, it's not positive definite. I can't lower bound it by a W1 term, so I'm not going to be able to get a W1 term that's radially unbounded. So the answer is no, not radially unbounded. Plus, we can just look at this graph and tell that it's not radially unbounded, right? Because as x2 gets bigger, it's saturated at pi over 2. As x2 goes to infinity, we're not going to get infinity out this way. Some people got confused about that it can go to infinity this way, but it needs to go to infinity this way. So x2 is saturated. So it's not radially unbounded either. So it's not positive definite, not radially unbounded. What about decrescent? So we've got, can we develop an upper bound? So I can write an upper bound as x1 squared, 2x1 squared, because the biggest this can be is 1. So I can get 2x1 squared plus, can I upper bound the tan inverse of x2 by some function of x2? And the answer is yes. You can pick some function of x2 that's greater than or equal to, oh, well, I don't even need to do that. I don't even need to do that. Tan inverse x2, I can just put absolute value of tan inverse x2. There's a function right there. It's always positive. It's a function of x1 and x2. This is a positive definite autonomous function. So yes, decrescent. Man, I may have missed that one, number 4. I have to think about that. Okay, so are there any questions about this problem in general? Okay. So the way I graded this is if you missed one of the choices, it was -2, and if you missed 2 or more, it was -5. All right, so then came the fun problem. You know, these first 2 problems were, you know, do you just know the rules kind of questions. And the third problem was, do you have the tools to start becoming an artist? You know, can you draw a circle? Can you draw the square?
Just real quick, back to this. I mean, number 4 is correct. I mean, the definitions just exclude the origin, but it doesn't mean it can't be one at the origin. Like it's saying this is the only place that you see it.
So, what I suspect is that Will is confused and then has confused me that he's thinking that V